Hello students, this is Rahmat Ali from Indirapuram Public School. In the last session we have studied about the force on a current carrying conductor placed in a magnetic field. We studied the force between the two parallel conductors carrying current. Now in today's session we will study about the torque experienced by a coil placed in a magnetic field. We will study about the moving coil galvanometer, how to convert a galvanometer into voltmeter and ammeter. We'll begin with the topic torque on a rectangular coil carrying current placed in a magnetic field. Let a rectangular coil KLMN carrying current I is placed in uniform magnetic field B, making an angle theta. If KL is equals to Mn is equals to length L of the rectangle and Mn is equals to Kn is equals to B, the breadth of the rectangle, then the force on arm KL is FKL equals to BIL. According to Fleming's left hand rule, this force will be radially downward as shown in the diagram. Force on the arm LM is FLM equals to BIB cos theta. Once again, according to Fleming's left hand rule, the magnetic force will be upward in the plane of the paper. Now the force on arm MN is Fmn equals to BIL. Fleming's left hand rule gives us the direction which will be radially upward. And arm NK is Fnk equals to BIB cos theta. Once again, using the same rule, we obtained the direction is downward in the plane of paper. From the situation, it is very clear that forces FLM and Fnk are equal in magnitude but in opposite direction. So they cancel each other, whereas the force KL and force Mn are equal in magnitude, opposite in direction. These two forces are forming a couple. One force is acting downward, second force is upward. The two forces form a couple which tries to rotate the coil. So the torque tau equals to force into the perpendicular distance between the two forces, which is B cos theta. Substituting these values, we get tau equals to BIL B cos theta. As we know, length and breadth are multiplied in the formula, so torque tau equals to BIA cos theta. Here A represents the area of the loop. If plane of the coil is making an angle alpha with the magnetic field, then alpha plus theta is equal to 90 degree. So cos theta will be equals to cos 90 minus alpha, which comes to be sin alpha. So cos theta is equals to sin alpha. Substituting this value, we get tau equals to BIA sin alpha. If number of turns in the coil be n, then the total torque tau will be equals to n BIA sin alpha. In the vector form, we can write it as tau equals to m cross b. Here m represents the magnetic moment of the loop, and the SI unit of this magnetic moment is ampere meter square. Moving coil galvanometer. It is a device which is used to detect the presence of current in the circuit. It works on the principle that when a rectangular coil carrying current is placed in uniform magnetic field, then it experiences some torque. Let's study its construction. It consists of a rectangular coil having n turns placed in uniform radial magnetic field B. The coil is wound on a soft iron core. If area of each turn in the coil is A, then torque tau will be equals to n BIA sin alpha. As the field is taken to be radial, so alpha equals to 90 degree. So the maximum torque tau will be equals to n BIA. Due to this torque, coil will rotate in the magnetic field. In the construction of a moving coil galvanometer, we connect a spring having force constant K. The spring is attached to the coil as shown in the diagram. This spring opposes the rotation of the coil. If at any instant the coil is rotated by an angle theta, then the restoring torque tau will be equals to K into theta. At equilibrium situation, the torque NBIA is equals to K into theta. From here, we can calculate I equals to K into theta divided by NBA. Knowing the values of theta, we can calculate the current through the circuit, because K will be given for a particular galvanometer, number of turns, magnetic field and area of the coil all will be constant for the given galvanometer. Depending upon the different values of theta, we make a scale for a given galvanometer to read the corresponding values of the current. Sensitivity of a galvanometer. It is defined as the deflection in the galvanometer per unit current. If current I is passing through the galvanometer and the maximum deflection in the galvanometer for the corresponding current is theta, then the sensitivity Is is equals to theta divided by I. Substituting the value of the current, we get Is equals to BAN upon K. In order to increase the sensitivity of the current, we increase the value of magnetic field B and we decrease the value of force constant K. By doing so, the current sensitivity increases. We do not increase area of the coil in order to increase the sensitivity. The reason behind it is that it becomes difficult to maintain uniform magnetic field for larger area. We do not increase the number of turns also, as by doing so the resistance of the galvanometer increases, which opposes the flow of charges through it. Shunt. As we know that a galvanometer is a very sensitive instrument, so it can be damaged when strong current passes through it. For safe operation of galvanometer, we shunt it. Now, shunt is defined as a small resistance which is connected in parallel across the given galvanometer so that the extra current will pass through it. The diagram is there, which is representing that a galvanometer G is shunted by a resistance S. If maximum current which can be measured with the help of a galvanometer is Ig and the current in the circuit is I, then shunt across the galvanometer S will allow the extra current I minus Ig through it. According to Ohm's law, the potential difference across the terminals of the galvanometer and the shunt will be same. If the resistance of the galvanometer is G, then I minus Ig into S will be equals to Ig into G. This is the relation which we obtained using Ohm's law. From here, the value of shunt S is equals to Ig into G divided by I minus Ig. Conversion of galvanometer into ammeter. We know a shunted galvanometer is called an ammeter when whole setup is enclosed in a box as shown in the diagram. As I minus Ig into S is equals to Ig into G, so I into S will be equals to Ig into G plus S. So the maximum current which can be measured using an ammeter, I will be equals to Ig into G plus S divided by S. Knowing the values of S and Ig, we can calculate the value of current I. Resistance of an ammeter. As resistance S and the resistance of the galvanometer are in parallel to each other, so using the relation of parallel combination of resistors, we get 1 upon A is equals to 1 upon S plus 1 upon G. That means A equals to G into S divided by G plus S. Always remember, an ideal ammeter has zero resistance and it is always connected in series combination of the cell. Conversion of galvanometer into voltmeter. In order to convert galvanometer into voltmeter, we connect a high resistance in series with the galvanometer. If R be the resistance connected in series with the galvanometer, then the total resistance of the galvanometer setup RV is equals to R plus G. So the maximum potential difference measured by the voltmeter V equals to Ig into R plus G. Voltage sensitivity. It measures the deflection in the voltmeter per unit potential difference applied across the ends of the voltmeter. If theta is the deflection in the voltmeter when a potential difference V is applied across its terminals, then voltage sensitivity Vs is equals to theta upon V. Substituting the value of V, we get Vs equals to theta divided by Ig into R plus G. As we know, theta upon Ig is current sensitivity. So, Vs is equals to Ig divided by R plus G. Let's study a numerical based on the situation. Let we have a galvanometer of resistance 50 ohm which gives us full scale deflection when 50 milliampere current passes through it. If we have to convert this galvanometer into an ammeter so that it can read a current of 1 ampere, then we connect it with a shunt resistance S. According to the Ohm's law, I minus Ig current will pass through the shunt resistance S. So, I minus Ig into S equals to Ig into G. Substituting the values of current I, Ig, S and the value of G, we obtain 1 minus 0.05 into S equals to 0.05 into 50. From here, the value of shunt resistance S is equals to 0.05 into 50 divided by 0.95. After calculation, we came to know that the shunt resistance S should be equals to 2.63 ohms. So, it means if we want to convert galvanometer of 50 ohms into an ammeter which can measure a current of 1 ampere, then we have to shunt it with the resistance of 2.63 ohms. Let's study another numerical in which we have to convert a galvanometer of 50 ohm resistance into a voltmeter of 5 volt when this galvanometer gives us full scale deflection at 50 millivolt. In this situation, the maximum current through the galvanometer Ig is equals to Vg divided by the resistance of the galvanometer. As the maximum potential difference Vg is equals to 50 millivolt, so Ig equals to 50 into 10 to the power minus 3 divided by 50, which is equals to 10 to the power minus 3 ampere. We know the maximum potential difference measured by the voltmeter V equals to Ig into R plus G. So, substituting the value of V and Ig and the value of the galvanometer G, we come to know that 5 equals to 10 to the power minus 3 into 50 plus R. So, that means 5000 equals to 50 plus R, that is R equals to 4950 ohms. It means if we want to convert a galvanometer of 50 ohm resistance which gives us full scale deflection at 50 millivolt into a voltmeter of 5 volt, then we have to connect a series resistor of 4950 ohms with the given galvanometer. So, today in this session we have studied the torque experienced by a coil. We studied the moving coil galvanometer, how to convert this galvanometer into an ammeter and voltmeter, and we discussed two numericals also. In the next chapter, we will study the magnetic properties of substances like diamagnetic substances, paramagnetic substances, ferromagnetism. We will study the hysteresis and the application of hysteresis loop. That's all for today. Hope you enjoyed the session. Thank you.